The following program is brought to you by Element 14, the electronics community where you can connect and collaborate with top engineers from around the world. Join now at element14.com/presents.
Hi, and welcome back to the Learning Circuit. In the last episode, I had William from KEMET on, and we dug a little deeper into the world of inductors. Well, today, William is back with us. Yay! And we're going to do some experiments with inductors. Hi, William. Welcome back. I'm so excited to have you on the show again.
It's great to be here, Karen. So today we're going to be using our power supply, our thermal camera, and oscilloscope, and we're going to look at three properties of an inductor. We're going to look at the electromagnetic interference of an inductor, the rated current of an inductor, and the saturated current of an inductor.
Great. I've got my Keysight oscilloscope here and my Tenma power supply. I am good to go. Let's do some experimenting. All right, so in the last episode, William and I were talking about crosstalk. William, can you recap the definition of what crosstalk is for us?
Yes, crosstalk is the unwanted transfer of communication signal onto other traces.
Right. So normally when you would want to measure this in your circuit, you would be looking at the actual circuit traces on your PCB, but William and I are not in the same location. Surprise! And we didn't really have a board where we both could have the same thing to test from. So instead, we're just going to hook up a few different types of inductors and use an oscilloscope to show the effect of having shielding or not having shielding on your inductor. So to do this test, I had to make this fancy probe here. Now, do you want to tell us about the professional probes versus this kind of janky looking thing that I made here?
Yes, so typically these are called H-field probes, and usually you'll buy them like this, and they'll come with a cable and an amplifier. We are going to make our own, and you can make your own very easily by using a coaxial cable, a 50 ohm coaxial cable with preferably a single rigid center conductor, where you make a small loop on the end and you connect the center conductor and the shielding to the shielding of itself, and then you cut a little notch on the very top. And once you do that, you can hook this up directly to your oscilloscope. If you have a SMA connector, then you'll need an SMA to BNC connector and measure emitted electromagnetic fields. And so that's what we're going to look at today. By hooking up our inductors into our function generator of our oscilloscope, we can see the type of noise that comes out of a shielded inductor and a non-shielded one.
So William was trying to walk me through making one of these probes and said, just grab some coax cable you've got lying around. So I'm like, yeah, I used to use bunny ears. I'll grab one. And so I cut my cable in half and I was going to start making it. And then I realized that, yes, this is not the connector that is on my oscilloscope. So if you're going to make one of these, make sure that you either have an adapter or that the cable you use has the correct connector to connect to your scope. And then, yeah, so mine did not have a solid core. It was actually stranded, so it was a little tricky, but you want to make sure that you solder the core and the shielding braid over here, so you gotta break that and remove some of the exterior cover. And then here, I wanna make sure that I removed all of the braid, but I left the insulator and the solid core wire, the core is still in there. So that's what you want your own to look like. This is not the best quality one, but it's gonna work.
All right, so first let's look over our function generator settings. So in our waveform settings, we're gonna have a square wave output at a 10 kilohertz frequency with a 10 volt amplitude. So it's gonna go from 0 to 10 volts, and we're gonna set our duty cycle to 50%. So we can verify this by hooking up our leads to the oscilloscope, and we should see a square wave come out. And right here you can see the square wave. So we're going to apply the square wave into each of these different inductors, and we can see the type of electromagnetic interference that comes out of it.
All right, let's start with, I've got a couple different KEMET inductors here. So I've got a 4.7 radial lead it's a ferrite core, right, or iron core. So this is non-shielded. And then I've got one of the SMD metal composite shielded ones, obviously much smaller here. So I'll start with the bigger one, the non-shielded. My red probe here is connected to the function generator that is part of my oscilloscope. I'm going to connect the other end of the inductor to ground here. So, all right, I should be able to just put my probe over. And there we got these big old spikes. So I'm pretty close here. What does yours look like?
Yes, so I have my coaxial or H field probe hooked up to the 4th channel, and then I have the 1st channel hooked up to the inductor, which is also hooked up to the function generator. And you can see that I get these spikes, and these spikes will correspond to the positive rising cycle of a square wave and a falling edge one. So we're not going to see a square wave anymore because the inductance is loading the function generator and causing it to look like this. On Karen's setup, you're going to see a impulse response, as we call it, and it's going to oscillate up and down. And this is happening because she's actually using a passive probe, and a passive probe has a series resistance and capacitance. So by adding an inductor, you created an RLC circuit.
Yes, I did not have the correct probes because all I had was the probes that came with my scope as opposed to the kind that you would want to use for a function generator. So we work with what we have on hand, right? Yeah, it works. We'll be able to see it. All right, I'm going to switch to the metal composite one now. So now, yeah, see, that's a whole lot smaller. So tiny, so tiny. And I have to get, it's hard for it to even pick up any noise at all. I can zoom back in, so this is where I was when I was getting the really big signal for the other one. Yeah, see, it's much smaller. So yeah, we can see that there's much less noise coming off of the metal composite shielded inductor than the ferrite core one.
And it's worth noting that, at least in my setup, I'm comparing two 33 microhenry inductors. So they're exactly the same value, and you can see that the signal going into it is exactly the same, but the response I get from the electromagnetic interference coming out of it is much smaller on the MPX or the metal composite inductor.
So in the last episode, another characteristic of inductors that we talked about is rated current. So we are going to do a little experiment here to kind of show that off. Now what happens when you go above the rated current, it gets hot, the temperature rises. So I have a thermal camera set up here, and I have an inductor connected to my power supply. So I'm gonna crank up the voltage and the amperage and show the temperature change. William, you gonna help me out with this?
Oh yes, we could test rated current pretty easily with just a power supply. So with the power supply, we're gonna make sure that we have it set to constant current mode. And in order to set it to constant current mode, we're gonna set the max current of the power supply to the value of the rated current of the inductor. So in this case, I have a 2.6 amp rated current inductor in my hand. So I set channel 1 to be 2.6 amps. And what we're gonna do is slowly crank up the voltage so that we change from CV, constant voltage mode, to constant current mode. You wanna give it a go, Karen?
Okay, so my inductor at 340 milliamps will have a temperature increase potentially of 20 degrees Celsius. So let's see if we can make that happen. So I'm gonna see if I can increase my current here.
Yeah, so first you wanna set your current to 2.6. And I'm gonna set my current to 2.6, and we're not gonna get the current draw that we need, but if we slowly increase the voltage, we'll notice the current start to increase, because you're gonna need voltage if you want current. So in my case, once I set it to around 0.7 volts, I'm gonna get a constant 2.6 amps going into this inductor. And it's already starting to heat up pretty quickly.
What happens if we increase it? I am not seeing a change in temperature. Oh wait, there it goes. It's starting to, wait, maybe? Oh yeah, it's starting to get a little warmer. It's now oh man, now it's getting real hot now. Ooh, I can smell it. All right, I cranked my amperage back down because it started to get really angry. Yeah, it got up to I think almost 150 degrees Fahrenheit. It's at it's around 120 Well, it got up to like 140, 150, and now it was sitting around 180 or 108. And I mean, the importance of this is that if you ever have your inductor in your circuit and it's got too much current running through it, and especially for too long of a period of time, it can overheat and either fail completely if it goes really, really bad, or it'll just compromise the integrity of the inductor and it'll shorten the lifespan. So you always want to make sure that you are operating your parts within all of their ratings according to the data sheet. So like William is using a different inductor than I'm using, so that's why his ratings are different than what I'm trying to go for.
Yep, it's always important to make sure, this will give you a good idea of how much your temperature will rise for your application that you're using these inductors for. So you could design around it and basically make sure, I would design under it.
Yeah. You always leave a little room for error. And again, you have to, so like I said, I'm in like a 70-degree room here. But if you're operating, like if you have this circuit outside and it's going to be in extreme temperatures, especially like extreme heat, that's going to change the way that the parts, react and behave in the circuit. You know, if you have this outside in like Arizona or something in 100-degree heat, that's going to operate differently than in this room here that's at 70 degrees. The last thing we're going to talk about today is saturation current. William, can you remind us why saturation current is important?
Yes, saturation current is important because it tells us how much inductance drops with current due to the core material type that's inside the inductor.
Okay, and William has constructed a circuit for us that we're going to use to demonstrate saturation current. So can you explain your circuit to us? Go over that?
Yes, so over here I have a circuit that allows you to put in a pulse input. So we're going to saturate the inductor by periodically putting a pulse. And then during that pulse, the current's going to ramp up. And then we can define the saturation current by how the current curve looks like on the oscilloscope. So for this experiment, we're going to need a power supply, an oscilloscope, and a board. So let's take a look at the board first. So first we have two input capacitors here that will be connected in parallel to the power supply input over here. And this will allow us to supply much more current than the power supply can handle. And then next we have a MOSFET. So this is the MOSFET that's going to turn on and off in conjunction with the pulse input that's going to get fed in from our oscilloscope. And then these two inputs will be our oscilloscope input. And we're going to be monitoring the current sense resistor, which allows us to see current in a voltage form on the oscilloscope. And these two are for your inductor. So we'll be connecting our inductors here, our function generator here, our oscilloscope probes here, and our power supply on this wire. The first inductor we're going to test is actually the ferrite core inductor, which I have right here. Hook that up to the inductor input, and we should be all set up to go now. So the first thing we're going to have to do is make sure that our power supply is set to 0.05 amps. For safety reasons, we don't want to have this circuit see anything more than that amount of current, especially not 10 amps, which this thing can output. And next we set this to 6 volts. So the power supply is set up now. So our waveform generator is set up to be a pulse. Our frequency is at 50 hertz. Our high level is at 5 volts. Our low level at 0 volts. And our pulse width is set to the smallest width possible because we don't want the width too large. If you have the width too large, then the circuit will be supplied with too much current and your whole circuit could start to fry or heat up too much. But we have our power supply set to a 50 milliamp maximum current output, so that shouldn't happen. But just in case it does, you always want this to be as small as possible. So let's start to run our test. And we can see that as we slowly increase our pulse width, which you can see on channel 1, we can see the current start to rise across the inductor. And this is being measured across the current sense resistor. So any voltage reported here, we can easily translate back into current using Ohm's law, which is V equals IR. So current will start to saturate once you reach this point in the knee where current starts to just ramp up consistently high, because now you have saturated your core, and you no longer have an opposing magnetic field, so then your current will just start to rise dramatically. So right here you can start to see that the current goes from linear to nonlinear, and that is the area where your saturation will occur. So we look at the measurement. Right now I have my cursor set to be around 2.7 millivolts or 3. And if we do our calculations with a 0.01 ohm resistor, we can see that this would be around 2.8 amps. And we go back to our data sheet, we can see that this roughly matches up to what we have. And I think this part is actually rated at 2.6 amps for saturation current. So there's a pretty good correlation with what we see on our oscilloscope using this pulse method to test for saturation. All right, so now I'm going to show you what it looks like with a metal composite inductor. Now, the metal composite inductor has what we call a soft saturation curve. So we're no longer going to see this spike, and it's best to just show you. So I'm going to hook up the metal composite inductor now and turn on the power supply, and then let's have this thing run again. So over here, we can see that with a metal composite inductor, no matter how high we go, it looks pretty linear. And I know for a fact that this saturates at around the same point as the previous one. So it should be somewhere over here. But because of its soft saturation curve, we won't be able to use this method to actually find saturation current. And same thing with an air core inductor, we're going to see something very similar where the current's going to rise pretty steadily on its own. So this method is really only good for a ferrite core inductor where we can really see the sharp angle of the change in current.
All right, well, those were some really interesting experimentations we did. So if you want to use some KEMET inductors in your future projects, William, where do they find out more information about those?
It's great to be here, Karen. Now, if you want to find out more information about inductors or how to use them, you can always visit KEMET's Engineering Center or follow us on any of our social media platforms on the links below. Now, I hope you learned something from these experiments, but you should always remember to stay curious.
Well, that was really interesting to be able to do experiments where we could actually see crosstalk and rated current and saturation current. Have you ever done an experiment to verify the information you found on a datasheet? Tell us about it on the Element 14 community at the link in the description. Happy learning!